Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are back in it with more vectors, and hopefully we'll get into like some matrices as well, because I'm a bit of a linear algebra / vector calculus type mood, and basically let's see how these two subjects work together. So hopefully you guys are doing well. It's Tuesday, so I'm just going to double check some things here. Just want to make sure that we're streaming on YouTube as well, just so that everybody in the YouTube fam doesn't feel left out. Okay, it does look like we are streaming live on YouTube, so that's good. But how you guys doing? So I thought I would just basically just jump in and just do some reading / do some problems too. So basically for me, like, my study habit is that I would look at the things that are important and try to see what they do in the examples, and then I would basically do problems afterwards. I gotta stop saying basically. I noticed that I say it a lot, or I repeat the word a lot. Okay, so we just skim through the pages here, because with planes, sometimes I have a little bit of a difficulty with them. Let's see. So we have the normal vector with the point in question, along with another point. So basically, we just need a vector in the plane. We also need a normal vector perpendicular to the plane. Problem. Distance between a point and a line. Actually, does this book talk about Stokes' theorem? I'm actually curious about that. Conservative fields, scalar, line integrals. Oh, it goes into Maxwell's equations. Oh, here we go. Here's Stokes' theorem. So we have to know about surface integrals. Actually, I haven't looked up line integrals. Maybe I should look that up. I know I did learn it in Calc 2. And I have two books here. One is the one I learned calculus from when I was in community college, and the other one, and this one I just found, because it's mainly revolve around vector calculus. So thought I should like give this book a look around. So let's see if we can look for line integrals here. Actually, I'll look at the index. Here we go, line integrals, page 180. I don't think it's going to be 180 because usually they count certain pages here, so. Oh, this is the Jacobian. This is page 145. Hey Famish, how's it going? What's the best part of your day so far, my friend? 1080. Here we go. Line integrals. I'm just relaxing for a little bit before digging into programming. What are you programming this time? Let's zoom in a bit. Let's take this. I want to paste it so we have like references. Okay, so let's see, evaluating scalar line integrals. Oh, they're having me work on some projects. Oh, okay. That's cool, that's cool. So we got an example of what we should see in a scalar line integrals. Let f be a continuous on the region containing a smooth curve. Okay. And these are the derivatives of I and t. Okay. Maybe I should move this over here. Explain mathematically why differentiating the arc length integral leads to let's see, evaluating the line integral. Okay, so I probably should capture this one too. Textbooks are not meant to be read, they're meant to be skimmed. I don't know if that's the right thing to phrase that, but that's usually how I think of it. Let's see, find the parametric description of C in the form of, okay, compute this, okay, and then make the substitution for x and y in the integrand. Okay, sounds straightforward. So we got an average temperature of a circle, and this is x and this is y, and I'm thinking we have to take the derivative of these with reference to t. So I'm guessing that's what we need to do. Then we have to basically do this first, yeah, because it says calculate this, and then basically put it in the equation here. Begin the appropriate substitution. I mean, this is about the same thing, but it's probably better to put this into. Spin it like that. So that way everything's in one place. They did it with the two-dimensional case. So we have 100 times that, and this is the primary function we're dealing with. So okay, I was like to say, where did the 2 to the second, where did the second power come from? And I was like, oh, it probably came from the original function. Different forms of line integrals of a vector field. Put this over here. Let's expand that like so. So according to this, different forms of aligned integrals, vector fields. One question is that what is t in this case? Let's see if I missed that detail. Oh, here we go. Yeah, we have a definition here. We might as well take the definition as well. Over here. Field. And let f be a vector field that is continuous on a region containing a smooth orientated curve C, parameterized by an arcing line. Okay. Let t be the unit tangent vector at each point of C, consisting of with its orientation. The line integral of f over C is the dot product of the tangent vector with the vector field. Okay. I guess like the fun way to think of it is like basically like think about I guess like a ground that's very, very bumpy, and then you use t, and t is basically like determining how smooth everything is. Let's see, maybe expressed in the following forms. So we have to take the vector field with the dot product of the derivatives of basically have to do, so f is equal to this. Following the orientation, let's see, a quarter of the circle of. So we have to evaluate this. So with the curves, we actually have to parameter, basically like turn x and y into like the sine function of these. The sine and cosine, I should say. Says x is cosine t squared. So I'm wondering why it's a t squared. Oh, okay, maybe it's because of this. I should also look up arc length too, because I think this is more related to arc length, or at least like it has a connection to it. So let's see if we can find arc length. Surface area. Supposed to be length of curves. Here we go, arc length. So I think we should start off with arc length because I think arc length is kind of related to the line integrals. So I think that would probably be a good starting point for us because arc length I haven't like fully solidified in my head because when I took Calc 2, I think my professor like kind of skimmed over it. Like we only went over it for I think like 2 classes, but then we never touched upon it again. So I was like, oh, okay, maybe I should like familiarize myself with this first before we go into line integrals. Okay, arc length. What is an arc length? Let f be the continuous first derivative of the. So we have a function, and we're supposed to take the derivative of it squared. Okay. Alright, so what does the arc length formula give for the length of the line? Y is equal to x and between x's. Okay, that should be a fun exercise. So I think we can take that. Because sometimes I like doing the quick exercises because they sometimes let us like work out our math muscles. I know I'm taking a lot of stuff from the textbook, but sometimes like when I'm on a computer I just basically just want to like basically just take the notes from the book and then just basically try to compile it in my own head so I can like look it over in like one whole lineup. Alright, so the arc length let's just familiarize of the notation. It's 1 plus the derivative of f squared. So, in this case, we have y is equal to, which is similar to saying that f of x is equal to x. But in this case, it's the derivative, so then the derivative of f is going to be 1. So then the arc length, so let's just erase that. So from x to 0, from x is 0 to a, means the arc length in this case is going to lead us to square root of 2 d. I should write that better. It's not a 12. It's meaning that's going to be x. Then we have a, so it's going to be a times the square root of 2 is the arc length. I mean, that usually the simple ones are the ones that you kind of like want to like actually feel like you had a grasp on. So I think like there we go. All right, so at least we did that right. Sometimes I like to give myself like little victories and a pat on the back, because sometimes when you do like the harder problems, you kind of beat yourself up but not being able to do the harder problems. Sometimes I'm like that too, so it happens to all of us. Let's see, find the length of the curve of f of x between, oh, let's actually try this problem. It's an example, but I want to try to solve it before, you know, I read the actual explanation. Okay, so to solidify our knowledge, we'll just write it all out again. Like that. Okay, find the length, so f of x is, so f of prime of x, so this will go down here, and then we'll have this minus this, which leaves us with because we're going to be left with a half, so that's basically what we gotta do with that. And then the arc length from, so we have a is 0 and b is 4, so from 4 to 0, 1 plus like so. This. So we have 9 over 4, and since this is 2 and it's multiplied by that, we're left with just x in this case. Now the difficult part in this case is that we have a square root here. Now, I mean, we could do u substitution. Let's try that. So if it's du dx, we'll be left with this. usually when I do integrals, I always forget this part if we're dealing with like fractional powers. I always forget something, and I know it's like something like this involved, so so it's gonna be half here, but then we're gonna flip it over. And then we're left with this. It's 1 plus. Just gonna double make sure here. Okay. So that if we do the arithmetic here, so we have 0. Well, if we have 4, then those will cancel out. Then we have 2 times 10 to the, like that, minus 2 over here. I'll be right back, guys. Alright, sorry about that, guys. But we're back. Okay. I think we can just do this on our calculator here. Parentheses in the right place. So according to this, we got 9.7. Because these 4s will cancel out, and then we're left with 10 to them. Just want to double check. Sometimes it's good to like work out the examples. this, and then that would be 0. Yeah, that would be left with 1 here. And I think we did everything right. Let's see what they have in the example here. Yep, it looks pretty accurate. They got 9.1, so they reduced it. So I mean, they rounded it up, but we got the same thing. So okay, that was pretty good. That was pretty good. Let's see, the arc length. Okay, so let's do this one. Let's do this example here. Okay, cool. I thought I'd cut off like some of the wording, but did it, which is good. So like that. Okay, so the arc length. So we're gonna have to do it from 2. This one's gonna be a little bit of a tricky one, because we have a lot of like exponentials in here. Oh no, then we have to take the derivative of this first. I can't forget about that part. So f of x is okay. So now that f prime of x, so I mean this stays the same. Oops, didn't mean to put that minus sign there. So this stays the same. This, I think we're gonna have to move the negative sign out here. So I think that's what we have. So it's that squared. Okay, now we're going to have to commence this complicated expression. So let's just write this FOIL out because I think it's easier for me to do so. If anyone can do it in their head, I give them credit for being able to do that. For me, I can't. Unless it's something very, very simple, then I can do it. But if it's not, then I have to actually do it, like write it out. Okay, so we got 4 like that, and then we got 2 times this, 2 times that. So the first one we'll do inside first, so that'll be 1 over 4. And if you multiply exponents, then basically you will have 0, which is 1. Okay. So then I think it will be the same for these 2. Then left positive 64. Then that will be -2. So in total, like -1/2 plus plus 64. Actually, we can probably write this to make it look nicer. So we can write there. And then -1/2. Okay, so that's gonna be quite... I mean... Oh, never mind. Like I was about to say, like, I don't have to put that under the square. I could just write it all out. So, it'll be 1 plus... Actually, let's put the half in front here because they're both... Hey Sascha, how's it going? So this will be a half plus are you winning? We'll see. I mean, we're doing a decent job of reducing everything. Like, so far we're just doing arc length right now. Because I want to cover at least arc length a little bit, and then basically go into line integrals. Because I feel like I can't really fully understand line integrals without going over arc length first. Question is, now the question is that can I reduce this? I feel like I can. Problem is Are you learning that from a book in electricity and magnetism? No, actually I just felt like I wanted to do a little bit of like operations involving vectors and matrices, but at the same time I realized that I don't know that much about line integrals, because like I was like, oh, maybe I should learn a little bit of Stokes theorem or something, but then I realized that I still am lacking knowledge when it comes to like surface integrals and line integrals. So I felt as if I should like kind of like brush up on the basics of those. So I think the one thing that looks like it's just that this part is kind of a mess because it's like it's all like an additional operation. I mean, we can't take a half out of there. So if you were to, so if you take 4 and then you basically divide it by a half, then basically technically it would be like flipped over. Oh, hello. Anku? Anku? Hopefully I'm pronouncing your name right. If I'm not, please, like, tell me how to pronounce it. I'm not able to understand the last step. Can you please revise it? Which step are we talking about? How are you doing, Anku? On YouTube. welcome to MathSpellBook. I think it's because, like, with here, I know I just basically factored it out, so it would be easier. Maybe I did an error here, so let me just double check here, because if we just multiply those two together, and then basically if you add those two, then basically that will be right there, and then basically when we add this with 2, that would be 1/4, and yeah, then when you have these two, it would be like plus x, x plus minus x. That would practically make it 0, so then that would be 1. But if we do it that way, it would be the same thing. Yeah, because they're both negative signs here. Uncool? Hopefully that's the right pronunciation. Yeah, I'm just double checking to make sure that I'm doing everything right. Yeah, these two negatives make a positive, and then yeah, these will be added together. Negative x plus negative x. That'd be negative 2 there. Alright, so yeah, we wrote it like this just to get rid of the negative sign there. Like the half minus 1, that gives us a half here. How did you integrate it out of there? Yeah, that's what I'm trying to figure out. I'm trying to figure out that Uncle. Like I'm trying to figure out the integrating process, or at least like how to do it in a way that's not as painful, I should say. Because we have a square root here, and that square root is kind of like ruining everything. That's the one thing that's annoying. And if we do like just use substitution, these will become very, very bothersome. I know that for sure. Like these two things here. I'm just gonna go back up to make sure. This one's a tough one, and it's one of the examples at the beginning of the book. Yeah, substitution won't work. I'm pronouncing it just right. Okay, cool. And by the way, guys, if it's your first time stopping by the YouTube live stream, you know, and if you really like math, physics, as well as just a study stream to keep you going, you know, consider dropping, like hitting the subscribe button. It really helps me out, as well as continues to motivate me to make more math streams for you guys. Yeah. Because I don't want to keep staring this problem in the face. Because I mean, that would be 1. curve are integrating over? Let's see. It's an exponential curve. Did what, uncool? What did you do? You want to take a screenshot, Sascha? What of the problem? Yeah, like I'm also streaming on YouTube, guys. Like if you're watching this on my Twitch chat, you can also go onto my YouTube channel if you want to like go back and follow along. Because like sometimes I do go fast, so just to let you guys know. Like I think on YouTube Live, you can, unlike Twitch, you can actually pull back the footage and then bring it back to live again. I just got to go through some algebra for a second. It's like, what does that have? What do I need to do? And then basically, like, x would have to be equal to 8. Yeah, it would have to be equal to 8 to get to a half, so. But it's still, like, kind of complicated. I mean... Maybe we have to write everything in, so I think what we can do, probably take this half out. And I think hold on. I'm getting way ahead of myself. I'm getting way ahead of myself here because what we have to do is that well, technically I didn't have to do this one. I tried the equation to get the to get what do you mean, uncle? Okay, so we have everything. tried the exact thing you are doing, but I didn't get the answer. Maybe there's a clever trick I'm not thinking about. What they did in the problem, because this is an example problem, so maybe I did something wrong here. Yeah, this looks super short. I probably didn't do a step here. Let's see what we got. Minus a half. Oh. Okay, so okay, so you have to be aware that you have to be aware that this is the addition version of this. Oh my gosh, that is a little maddening. Oh my goodness, we went through all this like if we wow. Oh my goodness. That's why it was so short. I was like, why is it so short? And I'm like, oh, it looks like... oh my gosh. So I guess we're gonna have to keep an eye out for those type of things. So apparently, this is just basically the addition version of this. Well, you know, sometimes mathematicians and physicists, they get into those type of problems where it seems like they got like a problem staring at them at the face, and then someone just walks in the room and says like, you do know that that's the opposite version of that, right? And it's like, wait, what? Oh man. Oh man, if I was like a theoretical physicist or a mathematician, I would probably be the mathematician that has everything in a complete mess, and then suddenly someone walks in and is like, you know, the pattern is like that, right? And I was like, oh wait, what? And they just solve it within 10 seconds. That's usually how I am sometimes as a person. I would get like a problem and I make it overly complicated without realizing it. But then again, you have to be like, I guess like I haven't developed my sight for like seeing like these type of polynomials. But that was actually a pretty interesting one though. It's a clever one actually, because like I was like, how did they make it so, how did they produce it so much? And it's like, oh, because it's the addition version of what this is supposed to be. I guess we're gonna have to keep an eye out for those type of mathematical surprises. Let's see, circumference of a circle. Confirm the circumference of a circle. Let's see, looking ahead, consider the parabola. So let's see the arc length of, oh, this one's for y. Usually I try to skim through like these sections because when the longer I read stuff, like the more I know my brain is not doing much, and that's when like I start to get sleepy, and I'm like, no, I can't have you guys seeing me sleep on stream. So like I basically skim through it to basically give myself room to actually just start working on stuff. Let's see, the arc length continues. Okay, so find the length of the curve between, okay, so how is this different? The solution? Zero, therefore the arc formula with respect to x cannot be used, and yet the appears to have a well-defined length. The key is to describe the curve with y as an independent variable. Okay, notice when whenever they work examples like this, I hate it when they bunch it up in one paragraph. I know it's like easy to explain this way, but it's like I'd rather like see it like all out like this. But then again, I don't think like you can have it all like that, like all nice like that sometimes. Sometimes it's just easier to just explain it like this. The arc like this one. Okay. Write the integral of the length of the curve of x. Where y is, okay, so we're gonna have to do this with y. So the way they did it here is that we have to take the derivative. They took the derivative first, and then what they did was they changed this up, and then they took the derivative of this. Right? Yeah, so it's y. Therefore, finding the length of the curve is usually with my streams, guys, I don't have like a specific order of like what I study. I just basically pick the ones that basically I'm like, you know what, I haven't even looked up this idea yet, maybe I should like look up this idea and start like, or this subject I should say. So x is sine of y. Oh, okay, so they already changed it for us. Okay, and y is, so in this case, x plus sine of y. Oh no, it has to be. We have to take the derivative of that. So, y. Oops. So x prime should be cosine of y, then cosine of y to the square by the y. So if that's the case, then cosine, then is that. Okay. I mean, technically, the question is that oh, Pound, how's it going? How's it going? What's the best part of your day so far, Pound? Unfortunately, for everyone that's on YouTube, I can't put your chat on the screen because I haven't figured out how to do that yet. Because like I actually have both chats like on one multi-chat window. The problem is that I don't know how to put, I guess, the chats from both platforms onto one chat. So, if you guys want me to read out what you say in the YouTube chat, I'll be happy to read it out for you. For like everyone that's watching on Twitch. Can't wait for summer to end. I hate the warm. I'm guessing. I think it's best for you to say you hate the heat. Now I feel you though, because it has been hot. And I will be streaming on my my gaming channel, my Uncle Talks channel tonight, because Genshin's getting an update tonight. It's gonna be pretty late at night though. So where was I? Oh yeah, so now should I transform this one into like cosine plus sine, cosine squared plus sine squared, sine squared? I don't think that would be the greatest idea though. Yeah, it's this. The square root basically makes things a little bit inconvenient. Or maybe I have to change the cosine squared into something else, because cosine squared seems to have a lot of identities. Maybe that's the thing we have to do. 1 plus, I think it was 1 plus cosine 2y. Oops, no, that's not x. Y. It's supposed to be y. But the truth of the matter is that does that even help us in this case? Because we can turn the 1, we can turn this one here into like 2 over 2, and then basically add that 1 to that 1 over there, and then we get 3 plus cosine squared. Maybe that might help. We could probably do a U substitution, maybe. Let's give it a try. If not, then I'll be making a lot of scribbles. We have a cosine in there. That's not gonna benefit us. Alright, so I mean, we can take the half out, but we're still back to where we started, only with a 3. I think this is the reason why a lot of people don't like math, is because like either they make small mistakes and they hate that, or they feel like they don't know enough of these little tricks to see like the, I guess like the more intermediate vision, like the intermediate mathematical vision. Because I mean, the last problem we got stuck because we didn't know that we can like reduce it to a certain form that we weren't used to, or used to when we see that type of form. But that doesn't mean we should give up on math though. I mean, I'm trying not to, but it's usually those small little tricks that make me nervous about like trying to do things like, you know, like going back to school for mathematics, because it's like, oh, I don't know enough about these little tiny tricks. But then again, they always say like do more problems, and when you do more problems you actually see those tricks a little bit easier. But it also depends on what you do math for, though. Because I think a lot of people do like solving puzzles, and I think like with math, like the more you have in your arsenal, the more you begin to become a problem solver. But it also depends on what your why is for learning math. Because my why is just to understand like the mathematical structure of our physical reality, or at least being able to model it through math. It in one term. The problem is that I think like the reason why I think arc lengths are pretty difficult is because of the square root. I know the square root is there for a reason, but it's like, dang, you're so cumbersome to get through. Because like integrating with the square root in it is usually the hardest thing to deal with. Is there a method I'm not thinking of? Maybe we should have written the one the way I thought about. My gut tells me that there isn't a closed form for the. Okay, I think we. Oh yeah, that's an example. Quick check. Actually, what is before this? This is chapter 6.5, right? Yeah. So we would have to know what integration is. And then there's the shell method. Yeah, there's a shell method and this slicing method. So we don't have to know that much. Like, let's see, integration. Yeah, we don't have to know like the integration techniques. So what is it that I'm missing? I mean, the only thing I can think of is I mean, we can take this out. I wonder if Quizlet has like the way to solve this. Library? Folders? Not this book. 6.5. No, they only have the exercises. guess we'll just move on to doing these problems. Let's see. Let's try number 7. Number 7 seems like it's challenging. I don't want to do problems that are just too easy, but at the same time, I also don't want to do problems that are like excruciatingly difficult. But then again, I'm probably picking the one that's the most difficult. So I guess we'll just do this one as a little bit of a challenge. No closed formula. It's like the length of a parameter of an ellipse. Alright, so this is y. So f of x is, this one's gonna be a doozy. So f prime in this case so let's see. Okay, x for this one. So we're left with times 2 square root of u, which in turn is 6 times x which leads us to okay, I think that's about right. And then that's all over 8. I mean all over 3. So technically we would be left with this. Because then we did this. That was 2. Right. And then okay, that looks about right. Now length, and we have it from 1 to 0, right? Yeah, 1 to 0. Then we have 1 plus square root 2 dx, which gives us 1 plus x squared plus 2. Then that leaves us with 3 plus x squared. This might be like a trig integral, but I'm trying to remember which one it is, because because the problem is that I think with the trig ones they have to be 1 over the square root of something, but for this one know if it's an anti, if it's supposed to be the inverse trig functions or it's supposed to be the regular trig functions. Because I feel like it's like the it's the inverse trig functions. But like the inverse derivatives. So let me see here. Let's see here. Oh no, these are 1 over. I would say it's a hyperbolic cosine of something. Could be. And here we go. I always forget these. Yeah, because the... Oh, okay, so tangent is like this. Okay, so probably not that. Substitution rule. Integration applications. Yeah, the square root always makes it harder. Jeez. If there was no square root, then basically we could just solve it like, you know, just regular. But unfortunately, it's not going to be that easy. And we haven't done like trig substitution either, or at least like trig substitution is like not covered until like the next couple chapters later. So I'm probably missing something. What am I missing? Because we can't do use substitution because how confident you are in your y prime. Maybe you're right. Maybe we have to double check that. Because let's see. Did u, and then basically we did take the u, bring it down, -1, that would be a half. And then we have to multiply 2 because we pick from here. So these two would cancel each other out. But I chose not to do that. Just make that 6 and then make that 3. And then basically all this term, because if we're taking the derivative, then this term would be over 3. And like 3 over this, that would leave us with 3 and cancel. I think we're fine. And then yeah, we're supposed to do that. Well, actually, let me just double check because that's for y. Yeah, it's the same. So bring this back down here. U being 2 doesn't mean that U is 2x plus something. Because basically we just took the derivative for U, and I mean for like the variable like that is within U, so that's why it's 2. And basically U here is basically this part. And I know you're supposed to multiply these two together. Maybe I did make an error here. Because there's the x is supposed to be here, which means we probably can't do this method, or maybe we can. Oh yeah, I think we can. So I think there's supposed to be an x here. So these two will reduce. Then we're left with this. Thank you for pointing that out, Pound. No problem, take your time. I guess this whole stream is basically just me doing arc lengths. So that means we're gonna have to rewrite this. Hopefully. Okay. I think we're getting somewhere. So this should be 4 plus So if we think about this, then I think it would be 2 plus, yeah, because let's try that, let's see what it ends up being. So if you do it like this, then that would be 4, and then that would be x squared, and then plus x squared, and then plus 1. Yeah, so 2x squared. Yeah, so that works. So then if we reduce that, we are left with x squared, x, yeah, there we go. That's the thing we want. So it would be x to the cube, then plus x, and then it's from 1 to 0. So then we're left with 1/3 plus 1 which is 37. There we go. I think that is it. That's what we were looking for. Oh, wait a minute, wait a minute. I think I made another error. Did I? Oh no, I don't think so. Because just gotta erase this part with x. There we go. Because that will be x squared, and then this done here. Yeah, because then we would have the x squared here, and then basically like x squared times that. And then yeah, I think that would be it. So let's see if we were correct here, because this one's number 7. Yeah, number 7 of this chapter. And this chapter is 6.5. Like curve, yeah. 6.5. So let's check on Quizlet. 6.5. Exercise 7. Yep, we got it. Okay. That's what was fouling up. So, if Pound is back, thank you for pointing out my error. Actually, that saved me a lot of time. That allowed us to get the right answer. Nice. So, what is... let's go down here. Let's see, we have 9. Let's see. Arc length by calculator. No, I don't want to do that one. Let's see, arc length with respect to y. Find the arc length of the following. Guess we'll do 23. Oh, no. I don't want to copy it like that, so let's do that again. So let's copy this. And we'll copy that. Paste. Then expand it like that. Okay, cool. Now, okay, so this one looks like it's going to be quite challenging. So, x. So if you take x prime here, so we're doing that over 4 plus. Let's put y as negative. So if it's -2, then minus. So this one will be -2 and y 3. So it will be. Then, well, actually, we should put a minus sign. Okay. Maybe we should try to. Maybe we should try to do this a bit like. Let's see. Now, is that accurate. Reduce that to this. For the difficult part, which is 2. So I think this bottom part would be 16. Power of 6. Then we're left with power of 2. Oh boy. Oh boy, indeed. May I suggest computing the square of the derivative on the side before setting up the integral. Having more space saves you in headaches later. Yeah, usually the problems at the end of those sections are usually the hardest. Because sometimes you never know what your professor's going to put on the test. But then again, I'm not taking a class. Usually for me, I just like to get through the basics, but if I see like a complicated problem, like I don't mind being challenged by it, but at the same time I'm like, dang, like how much knowledge from math do I have to actually put into this solving this puzzle? And if it's like knowledge that I completely forgot, then I'm like, oh my gosh, how can I forget this? And I probably will remember it like probably like when I'm sleeping or like when I'm like in the shower or something. That's usually how it'd be. especially later if you end up with a parametric curve when you are given x, y, and z, where the method is exactly the same, the root of the sum of the square of x prime, y prime, and z prime. Yeah. I'm surprised my professor didn't go over this a lot, because the thing of it is that she mainly focused on integration techniques. Like, I think we only covered like arc length like probably twice in the course. It was like I think like 2 classes on it, but we didn't really came back to it after that. Technically, we can write it like this. It's not squared, it's 6. Power 6. Hey Don, how's it going? We're doing some arc lengths. I thought we were gonna do some vectors, but I ended up doing arc lengths instead. If you like on Twitch, if you guys are not familiar with Don Fractorial, he's another awesome math streamer. He also plays video games on his stream as well. So if you haven't checked him out, please check out Don. There we go. Okay, cool. I wanted to make sure that I typed your name right. It's going well. Hope you're doing well. No, no, you're welcome. I don't know why I say thank you. I guess that's what I wanted to say, but I guess my brain got tongue-tied, or my brain made myself tongue-tied. So, yeah, we're doing some tough problems today. I mean, it was tough for me, but I'm pretty sure for chat it's probably like super easy. It's like, do this thing, do the thing, right here, this thing. So we're left with 4, and then if it's so, okay. Arc length is good to know. The general relativity I was trying to do. I was trying to build on that in a big way. Oh, okay, that's good to know. Maybe I guess that kind of inspires me to actually learn it better then. Because I'm learning arc lengths so I can actually learn line integrals. Like, I feel like they're kind of like similar. So like if I get used to arc lengths, I could probably get used to line integrals. That's the thing with me, like if it's like something branching off from like a similar math topic, I feel like I have to learn the basics of that topic first and then go into how that other topic works, even though they don't seem like they're related, but they function the same way, if that makes any sense. Like for me, it's like it was easier for me to grasp the idea of divergence because I already knew what a dot product was. if you guys understand what I mean. It's good that your day's going well done. Arc length is a line integral when you're integrating one. If you think about it, yeah, that's why I'm trying to learn this. Yeah, there's similarities for sure. You can bound the line integrals in part of the length of the arc. Oh, okay. Alright, so we got through this part. Now we have to integrate this. If this one wasn't here, we can just reduce it, but unfortunately we can't. I was thinking of U substitution, but I'm like, I don't think so. I don't think that would work. Yeah, it's that cumbersome one. It's like, but there's got to be a way for me to maybe not putting them together. Let's see. So if it's like this. +1 over. Then we'll be left with this. Then this. Yeah, maybe that might work. I just realized something, and I'm like, oh my gosh, it's been right in front of me. In general, whenever you're integrating 1 over a domain, be it an interval of 1 dimension, a surface, or a volume, you're getting the measure of the domain. Oh, okay. Like, I'm trying to visualize what you're saying, because like when you say measure the domain, I'm like, because I'm thinking of the domain as like a number line or like an axis, but mainly a number line like the x-axis. And I'm like, measuring the domain. Huh. So, yeah. Wait, do we have... Yeah, it's from 2 to 1. Or from 1 to 2, I should say. So, this side would be... So it would be 4 times 2. So 16 over 4 minus 1 over 4. Then we can add that with negative. It's 8 minus. That's pretty messy. Just write it like this. The domain of integration, for example, here you're integrating between 1 and 2. So your domain is the set 1 and 2. Oh, okay. Now in 1 dimension, it's a segment. Whenever you get to do double integrals, it'll usually be a portion of the xy plane. Oh, okay. Then, like that. So the first part would be 15 over 4 plus negative 32 minus, well actually plus oh goody. This is going to be fun. The old so then we're gonna have to make this 1 minus 32 plus 4 over 32. And then minus, that'd be 3 minus 32. And then we're gonna have to multiply by 8. Perfect. I just love doing that. Really, I do. Plus 3, 32. Then 123 over 32. Now, can we reduce that? No, we can't. Now, is my trick? Well, it's not my trick, but it's the trick that I saw. But I want to make sure that it's something we can do. Because since the square root is not there, I basically thought that, oh, maybe we can break it down to this, and I think it works. So I just want to see that the arithmetic works. Because I mean, with each integral, you kind of reduce it each. The only thing is that I could do the arithmetic wrong and then this answer is wrong. But usually with the arithmetic, I'm like, oh my gosh. Because usually for me, I get the method and the technique right, but I think the reason why I ended up hating math in school was because of the arithmetic. Because I had to juggle so many numbers around. And of course, like when you're doing a test, you feel like, oh, I just want to move on to the next question. Like, I don't want to check my work, but then like you get points by doing that, you know, just checking your work. But at the same time, you're just like, oh, I got the technique right, but I just didn't get the numbers right. But of course, like when you're a scientist, and if you're a scientist and you're like making measurements, then obviously you have to get the measurements right, otherwise like things could go haywire. Correct by linearity, the step where you just rewrote everything, took out 1 out of 4, made me suffer a bit. What's NGL? Sometimes like with texting terms, like I always forget like certain things. Like, you know, like WTF, everyone knows what that means. I guess we can check, because this one's number 23. We probably got the numbers wrong, but I feel like maybe the technique is correct. Not going to lie. Oh, okay. Table of contents. 23. Moment of truth. Yep, that's the same number. Okay, because sometimes when I use Quizlet, they put like old numbers from like a different edition, even though it's supposed to be this edition. But it looks like it's the same numbers we're dealing with. And we got it right. Nice. Whew. That got me nervous. That got me nervous a bit. But we got it right, guys. This part, I think this part I'm most proud of. Like, this part, breaking it apart. I'm like, oh my gosh, maybe we can break it apart. And I'm like, wait, it works. It works. Yeah, I mean, you guys will see me like struggle with problems and get problems wrong sometimes, but when it's moments like this, I'm glad you guys are here with me on the ride. It's like this, which part? Let's see. Bring it up here. This part, oh, I meant to circle it here. This part, I think I'm the most proud of. Because I'm like, wait, it works, because there's no square root that's in the way, and I'm like, oh, okay, so let's do that, and lo and behold, we got it right. But yeah, I'm happy about that. Cool, and I think that's a good way to end the stream today, guys. We got like a problem right that was very difficult, well, challenging actually. Because I'm pretty sure it probably wasn't difficult for you guys at home, but for me, it felt like it was really challenging. But I felt like I learned a lot from that one. But what else is there? Oh, there's a word problem with arc length. Maybe I also should cover hyperbolic functions. I have never done hyperbolic functions ever in school. I don't know why. They never really covered it. I guess maybe it was because it was too far in the curriculum. Back in the day, I used to do multiple passages in my mind, and either my teacher hated me or bashed me for making mistakes in there. Yeah. I mean, like for me, it's like I have to actually like be able to like look at a problem and see what it is that I need to do. And sometimes when I see a problem and I don't see the right way to do things, I end up like feeling like I have to step away from the problem. But of course, like when you're in school, you can't do that. Like usually they just make you like sit there like twiddling your thumbs and like you're trying to figure it out and you never figure it out because you're just pressured to get the result. Which is why I like doing math as a hobby, not doing it as an obligation. I mean, it would be cool if I can like, you know, help teach or tutor, but like for me, I feel like I have to learn more, and I think like the small stuff I can tutor, like maybe like algebra and stuff, but when it comes to like calculus and stuff, I feel like I have a long way to go when it comes to like learning calculus. Even though I do know Calc 1, I still have to learn more about Calc 2 and Calc 3. and then differential equations too. Okay, so I think that will do it for today, guys. I probably will change the title of this on YouTube to like arc lengths instead of vectors and matrices. Because I realized that we didn't do any of those. We just did like arc lengths in this stream. But thanks for joining me today, guys. We will be back tomorrow. I don't know what math topic we'll cover tomorrow, but anything that my mind is curious about, hopefully you guys will be able to join me for the ride on that. Maybe we'll probably cover more on arc lengths, and maybe we'll probably go from arc lengths to line integrals. Maybe that will probably be our starting point for tomorrow's stream. But yeah, this was a lot of fun, and the challenges were quite rewarding. But yeah, always remember, guys, everyone is precious. You guys are just as precious as everyone else. And I will see you guys in the next stream. So take care, guys. Bye-bye.